Okay, so thanks very much for inviting me. I'm a research scientist in Google Deepmind in London, and I'm going to talk to you about the work of many people about how do we scale machine learning models, and I'm going to focus on training. Really, I'm going to try to teach something to people about how, well, what do we mean by scaling machine learning models? How do we actually deploy them on accelerators? And we're going to start with the basics, really. And the basics is, what is a machine learning model, really? A machine learning model, you can think of it as, from a systems perspective, from a compiler perspective, you can think of it as a program. It's an ordinary program that encompasses the numerical computations that you see when you train or serve a machine learning model. So these programs involve n-dimensional arrays. They include the linear algebra operators. They include, typically they have static array types, meaning you fully know the ranks, you fully know the dimension sizes. And typically these programs are generated through tracing Python from high-level frameworks. Like you start with a program like that. It's a training step, takes the parameters of the model, the optimizer state of the model, and some samples, the next batch process. It computes the gradients with respect to some loss function with respect to the parameters, gives you the gradients for the parameters, and then you apply the optimizer on these gradients and the original parameters and the optimizer state, and you get a new optimizer state and the new parameters, and you keep going. And you return this and you keep going. And literally, all machine learning training that you see out there has a loop like that. The interesting thing is that while Python can be very dynamic, it includes kind of mutation objects. The programs that are getting traced out of this function, for example, they are purely functional, no side effects, no heap, no state. They're kind of easy programs. So they're easy to optimize, easy to reason about, and should be easy to partition, really. So I'm going to pause a little bit. I want to see hands raised for how many of you have taken a compiler class in your undergrad or grad or something. So there is a small percentage, but not zero. Okay, cool. So there's going to be a little bit of compiler in this talk, but I'm going to try to cover the basics. Another introductory class, and I guess all of you know about backpropagation, right? How many know about backpropagation? Okay, cool. So now we're going to think a little bit about backpropagation as a program transformation, because that's what happens in these frameworks, right? So you see the program, here's a very small program that computes the dot product of a tensor x or W, weights, tensor x and tensor W. So W, you can think of them as the weights, x, you can think of them as the activations. What happens is in this program you call jax.grad, which says, give me the gradients of this loss function, and jax.grad of a function transforms the loss function into another function, really. That's what it is, a higher order transformation. So basically, you start from this function, which is just a dot product, and through a sequence of transformations, you get to a program which contains the forward computation, as you sometimes people teach it, of backpropagation, some residual activations, which are what is stashed, what is saved, or the tape, as some people call it, and the backwards propagation, the backwards part, which really computes gradients by running the network backwards. The interesting thing is that the backwards computation computes gradients for the parameters and gradients corresponding to the original input of the program for backpropagation to continue, and so for this to become compositional. So in terms of a program transformation, you get, this is the yellow part here. You see the yellow part here, which is the forward part, and these green stuff are the backwards parts of the program. I just want to give you a bit of a flavor about how these things look like. So okay, we have these kind of programs. These are nice mathematical abstractions of the training. They are runnable. You can actually take this program and you can imagine running it on a CPU or on a GPU. But obviously, as the models become larger, you need to think about how do you take a program like that and you make it run on many, 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 many devices. So why would you do that? Well, this is a graph from our world in data that shows that the compute cost for training large machine learning models has skyrocketed, and it has actually crossed the 10 billion petaflops to train it from end to end. And just to give you an understanding, what does that mean, really? That means that you get 4,000 NVIDIA A100 GPUs, which is not the top of line, but it's a very beefy accelerator. And you have them train, these 4,000 devices, you have them trained continuously for 3 months. And that is assuming that they all operate at peak compute utilization. They give you 312 teraflops per second. You have no communication costs, which is impossible to not have communication costs because you need to synchronize 4,000 devices. And also ignoring system failures and restarts. When you have this kind of deployments in data centers, things will fail at that scale. Servers will fail, network cards will fail, software will fail, some random sysadmin task will schedule an operating system upgrade, and this is time that has to be taken into account. Okay, so okay, we build these big accelerator systems and we train these large models in accelerator systems that look like that in data centers. You can see, big racks with special interconnects, possibly special cooling. But what is really important for you to understand is that there's a lot of complexity. It seems a bit magic, these accelerator systems, but there are like 2 things that are essential. One thing is that accelerator system is basically, you can think of them as devices. These are the actual devices that offer you beefy matrix multiplications, for example. They contain some sort of local memory, matrix multiplication, vector operations, and there is the system around it, the topology around it, how these devices are interconnected. And for example, here's another figure from a Google Cloud offering. You organize these accelerators in pods of devices. Each pod may contain hundreds or thousands of devices. Within a pod, these TPU devices, these accelerators, are connected through a very fast interconnect network. And across these pods, the devices can talk to each other through the host network. So there's a bunch of hosts that actually own these devices, own these trays. And you go through the data center network to talk across pods, for example. And this is just some papers that I'm throwing here, mostly for reference for people who will see the slides that kind of outline a little bit about the architecture of these TPUs. So, okay, let's start talking about parallelization a little bit. So the simplest form of parallelization is data parallelism or batch parallelism. How many have heard of data parallelism before? Okay, I would expect a few more. But essentially, what happens here is that you want to run your model. You want to train your model on 2 devices, for example, right? So you need to compute gradients for the parameters on 2 devices. So you split your batch, really, and you run the full model on each of the devices. So forward and backward, as I said before, forward and backward. What you do here is kind of an interesting step, is that you have calculated gradients for the parameters from the first microbatch. You have calculated gradients from the second microbatch, from the second split of batch from the other device, and you sum them together, and you distribute the sum again on the 2 devices, and the 2 devices apply autonomously, independently the optimizer. This is kind of one way to do it. You could do it other ways. You could share the optimizer. I'm not going to go in detail. But there is this collective communication operation here that's actually important. And now you start seeing, we start talking a little bit about the various trade-offs, because you have extra communication time that arises because of this communication that you have to do. Also, another interesting question is, with this kind of parallelism here, the parameters are actually deployed, they live on both devices. So if your model becomes really, really, really big, and your accelerator or device doesn't have enough memory, what do you do? So when you start taking kind of these kind of examples, and you start thinking about, okay, instead of 2, make 4,000 devices, through potentially slow data center network, or maybe and make sure that the model, for example, is a 500 billion parameter model. Batch parallelism alone is not going to cut it. Now, I want you to kind of reflect a little bit, to use the terminology of the previous speaker, on do people know why we do this all reduce operation here? Why is it correct to do an all reduce on the gradients? Why don't we have the devices operate kind of completely autonomously, and then maybe do some kind of weird fudging of the parameters that we get from each of the devices, or some other communication form? So we're going to try to answer this question in a little bit. But I want to raise the question so you can start thinking about it. Okay, so from 2020 onwards, there have been various, so okay, I described, basic batch parallelism, and it's not practical if you're going to train on 4,000 devices or 16,000 devices or something, because you're going to be like really beaten by the communication time to do this huge all-reduce operation, or reduce operations really, or you don't have enough memory on a single accelerator. So there have been several strategies that emerged in the literature, and I'm outlining some papers here, and they're really motivated by the need to train to scale LLMs. That was the forcing factor. So data parallelism is one. Megatron style parameter sharding, you can shard the parameters in various ways, or optimizer gradient sharding are another, activation sharding, pipeline parallelism, many strategies. They were typically easy to describe at a high level, and they composed well. So you can see some interesting papers on composition of these strategies. So I'm going to show you a refinement of data parallelism, which you may have heard in the literature. Sometimes they call it a 0-3. And I think in the PyTorch or Facebook kind of more world, it resembles more the fully sharded data parallel training. So we described that in data parallelism, we have forward, backward for every device, forward, backward for every device. We reduce the gradients across them, and then each of the devices applies the optimizer. So that means that the parameters are live on both devices, on both or need to be downloaded or streamed on both accelerator memories. But what if we did the following thing? What if we also sharded the parameters into two pieces? So device 0 gets a shard of the parameters, device 1 gets a shard of the parameters. But before and right before we actually need the parameters, we perform an operation to gather them. Since the batch is sharded, you do need the full copy of the parameters to calculate, let's say, a matrix multiplication. But what if we don't have the parameters reside in memory all the time, but rather we just transiently do an all gather and use them in the corresponding matpools, and correspondingly the backwards parse right here do an all gather, get all the parameters together, and compute the backwards pass when we need them. And then instead of doing an all reduce operation, you take the gradients of calculated in one replica, the gradients in the other replica, and you sum them together, but you give a slice of the gradients on one device that corresponds to the first chunk of parameters, and a slice of the gradients to the second device. And that's actually a cheaper operation that's called all reduce scatter that can be implemented more cheaply. So basically, you should think that the cost of an all gather, of an all reduce, is really the cost of an all gather and a reduce scatter. But then the optimizer as well can operate sharded now, because the optimizer has a shard of the parameters and a shard of the gradients, and you can get a shard of the new parameters, and correspondingly the other device. So now, okay, what have we gained, right? In terms of network time, we probably made things a little worse, actually, because you have an all gather here and a reduced scatter, but you have other all gathers as well in the backwards pass. So you trade off a little bit network time, but the parameters do not live on the devices all the time throughout the lifetime of the forward and backward, and the optimizer update is cheaper. So that's kind of one example of a trade-off that you do by changing your sharding strategy, your parallelization strategies. And just to tell you something, usually the optimizer, as you know, the optimizer contains typically as many or maybe double the number of parameters of the actual model, because it needs to keep momentum and learning rate and various other parameters. So actually, making sure that this thing here holds on to fewer parameters is actually quite important. So really one other benefit is the benefit, there is a drop in memory here because the parameters are not kept in memory all the time, but there's a huge benefit here in the optimizer. Cool. So there are more techniques that have been developed. So model parallelism, for example, is a different type of strategy where basically you can have multiple forms of model parallelism. One of them is pipeline parallelism, where you take you separate your neural network into stages. Each stage comprises of a few layers, and you start piping in microbatches on the stages. So this was the first 4 layers, the second 4 layers, the third 4 layers, and the fourth 4 layers. And this is microbatch 1. So you break your batch into microbatches, and you start streaming them through the network. And you do the same thing correspondingly in the backwards pass. And then you issue an update of the parameters independently without any communication across all devices at the end. So for example, what's the trade-off of that, right? The problem with that is that you have a bubble in the middle. So you need many microbatches to make sure that the bubble is small. You need to stream many microbatches. But for example, you avoid communication across all of your devices. You only have sort of point-to-point communication. These devices talk to these, and these, and these, and these, and these. So you don't have all reduce. So you have different types of costs in terms of communication. And you can actually hide the cost, because while this device here is sending the data to that device, it can already start executing the second microbatch. So there's good overlap of communication and computation. And then there are other ideas. If you heard of Megatron sharding, this is kind of the de facto training setup for large language models these days for parameter sharding. It breaks down to the bare principles of it is that you have like two matrix multiplications, and if you shard one of them along the columns and the second one along the rows, you can actually have one device calculating a smaller matmul and another device calculating another smaller matmul, and then do an all reduce operation across them. So now the all reduce is not on the gradient space, it's on the activation space. It's as the activations move forward in the network, you have all reduce, all reduce, all reduce, all reduce. Here, what I'm showing down here is that this is a variation of pipeline parallelism, where basically you don't get a bubble anymore. It's a fully dense schedule. So you don't have the bubble. So it's a recent paper. You can find it if you look it up. Zero bubble, and so it's a fully dense schedule, and it trade-offs compute efficiency, no bubble, but it requires much more memory on the devices because, for example, if you look at F7, when the forward microbatch 7 runs on this device, the saved activations that we discussed, the tape that we discussed for backpropagation, has to be kept live all the way until it is needed in the backwards pass here. So the distance between when you create your stashed activation from forward and when you use them in backward becomes really big. So it's another trade-off. So partitioning and distributing is full of these trade-offs. So you need to find ways to tame this space. So, poor Homer Simpson, he's read all the papers, right? Data parallelism, parameter sharding, activation sharding, pipelining, 0, 2, 3 sharding, fully sharded data parallel. And, we're given a model, we're given a system. How should we do it? There's another type of problem, especially when it comes to big companies and infrastructure provisioning, which is you have a system designer here, and the system designer is getting an architecture from the chip designers, from the hardware architects, and it's getting potentially some known models and maybe some unknown models, and it's getting some possible parallelization strategies, and basically they need to decide, okay, how should I assemble these accelerators into systems? How much memory should I add on each accelerator? What kind of interconnect should I use within my pod? What kind of type of interconnect? Should I use a mesh? Should I use a ring? Should I use a switch? What should be my host and rack connectivity? How large should I make my pod, basically, my fast interconnect versus the slower host network? And the key problem here for these guys is that one must not penalize a system design. By the way, these guys want to optimize not the hardware utilization, how fast they will kind of reach their final loss function. They want to optimize performance per dollar spent, basically. And the key intuition here is that one should not penalize a potential system design, a candidate system design, because of an unsuitable parallelization strategy. So, if you say, we go to the system designers and we say, we want to train a model on, in a data parallel fashion on 30,000 accelerators. That's kind of a joke, that parallelization strategy is just not suitable. So you need to think about jointly the parallelization strategy and the system design. Okay, right. Okay, so how do we manage all this complexity? So the canonical, I think one of the more fundamental ideas that kind of really originates in high performance computing, not in this machine learning stuff, to manage this system complexity is to abstract systems by using meshes. So you can think of you have some system like, for example, a GPU cluster where you have 4 GPUs connected on one host. There's a fast interconnect network in here, and there's another fast interconnect network here, and a slower data center network that connects the hosts or maybe directly the GPUs with NICs. You can think of these devices are basically a 2-dimensional array. And I'm just giving them random names here. I'm calling one dimension of this array as batch and the other one as model. And JAX gives you the ability to get the available devices of a system and reshape them, view them as an n-dimensional array, and name the axis that you're talking about. So, or you can have potentially, here's potentially another system that looks maybe more like a grid or a mesh, and you can also view it as a 2x4 device. So these meshes allows us a little bit to basically treat these devices, instead of talking about which part of the computation goes in each device, they allow us to talk about how do we map a computation onto an abstract mesh, something that has 2 axes, one size 4 and one size 2, for example. And the dimensions of these meshes, like, here you have 8 devices, right? Why did I pick this mesh? I could have picked any mesh. So actually, you can pick any mesh you want as long as you have communication across the devices of the meshes. But usually, we tend to align the meshes that we use for training with the physical topologies. Because that gives us an easy way to reason about the communication costs on different axes. So for example, if I want to communicate across these 4 devices, that's very fast. So, and these 4 devices. But if I want to communicate D0 with D0, D4 here, D1 with D5 here, D2 with D6 here, and D3 with D7 here, that's going to use the network, the host network, the data center network, and that's going to have a very different bandwidth and latency characteristics than the interconnect communication. And actually, the fact that I'm using these 2 axes here accurately reflects that. Communication on this axis is fast. Communication on this axis is slow. And I know their bandwidths, in effect. I know the aggregate cross-sectional bandwidth. Cool. Right. So strategies compose very well with through the use of meshes. So for example, here is a 6-stage pipeline parallel program where every stage has been sharded 16 ways. We have done parameter sharding 16 ways, and we have done 64-way batch parallelism, so the data is split. So along the columns here, each column represents, let's say, one replica of the full model, but each row within that column has a different shard of the parameters of the model. And you can see that when you are going to be doing all reduce on the gradients, you're going to be doing all reducing across these axes here. And when you're going to be doing all reduce on the activations for Megatron, for example, you're going to be doing all reductions like here. So they are sort of independent, and you can independently reason about them. And by the way, the point-to-point communications are this device talks to this one, this talks to this one, this talks to this one, this talks to this one. That's the pipeline. So really, this concept of meshes, and this is called single program, multiple data parallelism. It's a match made in heaven. It's like it really works very nicely. I'm going to tell you a little bit about sharding. How do we? Okay, so now we go back to the program, right? We have that program, and we have our mesh. How do we even express that the program is sharding? How do we rewrite the program to be sharded? And the first thing that we should talk about is how do we express the sharding of an array of a value over a mesh? So in this example here, you have a mesh X of just 4 devices. And here you have a tensor, a 2-dimensional array, 32 by 32, contains float 32 inside. And here we see that we have sharded along the columns. So every column here is 32 by 8. And we represent this by saying the sharding of this array here is nothing for the first dimension. We haven't sharded really the first dimension, but we have sharded the second dimension along axis x. So this corresponds to this first dimension, and this x corresponds to that second dimension. So we're just inventing a notation here to talk about sharding. And if we have a two-dimensional mesh here, so we have a mesh where x size 4 and y has size 4. So here we have like 16 devices, not just 4 devices. The array is the same, for the sake of the example, for 32 by 32. And here I'm saying, oh, please shard the first dimension on x and the second dimension on y, on the axis y. And what you see here is that you see that the device 0 gets this chunk, device 1 gets that chunk, device 2 that chunk, 3 that chunk. So this is the assignment of the chunks of the arrays onto devices 0 to 15. And each individual chunk of that array is 8 by 8. So that's the notation we're going to be using. And partitioning really happens with 2 compiler passes, right? This is just 2 compiler passes. One compiler pass is someone gives you some sharding annotations, or you have a tool or an agent, AI agent, discovering sharding annotations. And the step 1 is you propagate it through the program based on some rules that we're going to get back to what these rules are. So for example, here you have a mesh of just 2 devices, batch. And someone has annotated this x device, which is 4 by 30, x array, which is a tensor 4 by 32, and says, okay, the array should be sharded on this batch axis, on the first dimension. So really, that means that every device should have really a chunk 2 by 32. Should hold a 2 by 32. So what do? We start propagating this. We see, how is x used? Well, x is used here, in this dot operation here. And we see that x is sharded on the batch axis, and y, the w, the parameter, is not sharded. So we all know that if you have a matrix multiplication and you shard and you take a chunk of the first input that includes some rows of the first input, and then so if you split the first input on the rows, you can actually compute the matrix multiplication with the full parameters, and you just need to stack the results on the rows again. So this is why we said the result of this dot should also be sharded on this batch dimension. And then we continue and we say, okay, how is this, where else is x used? Well, it's used here in another dot, another multiplication, and that propagates to this variable here, which was another input of the function. And then what happens? Then this ctout, this variable, has now been annotated, so we propagate this further, and we get to this sharding of this dot general. And I think, yeah. And now, basically, we have sharded all values that contained this kind of this dimension of size 4. We know that they are sharded by axis batch. So that was the first step. The first step is just propagate everything, right? The second step is do code generation. Like, we actually need to rewrite the program to be a smaller program to operate on these chunks. This is the SPMD program, like the program that's going to, the local program. So what do? Well, we basically almost literally transcribe each of these annotations into something smaller. So here, x was sharded on the batch axis, so we know that the first dimension should be of size 2. Ctout was similarly annotated, so we know it should be 2. The dot product here should be of size 2. The dot general here was kind of interesting because the dot general was not annotated, but both its inputs, ctout and x, were annotated. And in fact, they were annotated on the contracting dimension of the dot general. And that means that when we do code generation for this dot general, we have to introduce an all reduce along the specific axis that the 2 operands were sharded on their contracting dimension. And basically, we continue. The rest doesn't have anything interesting. So step 1, propagate the sharding annotations. Step 2, take op by op, look at the sharding of the operands and what is the sharding of the result we have identified, and generate code for it. And this is pretty much the strategy of the de facto partitioner at Google, GSPMD, and the new partitioner that we're developing together with the GSPMD team. actually, you can have multiple access now. So you have the program that contained this batch sharded X, and you say, oh, I actually now want to shard my parameters as well on a different axis, on a model axis. So you add some more sharding annotations, and you propagate these. I'm not going to show you the detailed propagation of these. And you have this annotated module, and then you lower this annotated module, and you get maybe some more collectives, more communication, collective operations. So this is kind of roughly the idea. Now there are interesting issues that happen very often. So the main thing, one interesting thing that comes up is propagation conflicts. So here you have X, the activations, which is sharded on the batch axis, as we described. But you also have W, which is sharded on the batch axis as well. So both the input and the parameters are sharded on the batch axis. So the problem here is that if you think about matrix multiplication, the first operand is sharded on the rows, fine. The second operand is sharded on the same axis on the columns. So what should you do? Should you potentially ignore the sharding of the second operand and produce sharded the result of dot on the first dimension, like here? Or should you try to slice the first operand as well on the contracting dimension and shard the dot general and produce a null reduce? So this is a situation that we call a conflict. And the conflicts are typically resolved they're resolved in two ways, really. In GSPMD, kind of the rule partitioner, they're resolved sometimes using heuristics. So the partitioner is going to look at the shardings and is going to make a local choice about how to resolve them. But in our project and in the new version of this partitioner, we use propagation in rounds. So instead, we ask the user, would you like to do batch sharding first and then model partitioning, or model partitioning and then batching? And this priority naturally resolves conflicts, this serialization. I think I'm going to skip this slide. So the other interesting bit that comes often is internal conflicts. So how many of you know the architecture of a transformer, like a self-attention layer? So raise hands for those who have seen it a little bit. Okay, great. So we have activations coming in the transformer, and we need to compute the keys and the queries vectors, right? And here the activations have a batch size, a sequence dimension, a context dimension, and the model dimension. And assume that we have sharded this sequence dimension, right? Now, we're going to do a multiplication with the weights that correspond to the key construction to get the keys. And we're going to get out a tensor, the key tensor, which is sharded on the sequence dimension. Similarly, for the queries, we're going to do a multiplication and we're going to get the queries, which is going to be sharded on the sequence dimension as well. Now, we're in trouble because the attention matrix is effectively, an outer product of these two queries and keys. So it needs to have 400 by 400 dimension. But which 400 of the two, which sequence dimension should the one that should be sharded? How should we shard this attention calculation? And that's what we call an internal conflict. And here, what is interesting is that priorities wouldn't help. We only have one input to the function, and it's only by means of the user going inside the model and saying, please keep this replicated, do not shard it right here, in order for this sharding to propagate, or vice versa. That's the only way that you could resolve this conflict. But we do have some automated way of understanding these internal conflicts as well that I'm not going to cover in this talk. Okay, so given the lack of time, I'm going to think carefully about what to skip and what to miss. So this is what I described is more or less how GSPMD, the standard partitioner of Google, has been working. And around 2021, we were not in legacy Deepmind. We were not satisfied with the way it was working at the time. There were many reasons that we were not satisfied. First of all, the propagation was not as clean as I told you with mesh access. The propagation was actually using logical device IDs. So it was a much more low level. And instead of having meshes, you would have many big lists of device IDs in the programs. So when the programs became, or when the partitioning became really big, this became non-scalable. There was also a notable need for internal annotations to resolve conflicts because there was no priority. There were heuristics in partitioning and code generation, and there were actually discrepancies with propagation. So the propagation system would assume something, and then the code generation often had to create patterns that matched what it was expecting from propagation. It was not universal, so to say. Also, it was a little bit unclear what were the principles of propagation, right? I kind of informally explained to you like why we propagated this batch partitioning, but what's the principle behind it? And also, there were various engineering reasons, which was that the partitioner was built inside the compiler, the XLA compiler, and it was like very difficult to go and modify anything about it. And we also needed to think about automatic partitioning. So we built a system that we called PartIR, which has been the de facto partitioner in Deepmind until recently, because we're building a new generation of the tool. It was an external partitioner pass. It was not built inside the compiler. It had a unified propagation and code gen. So instead of doing propagation and code generation, it at the same time propagate and rewrote the program to be a partitioned program, if you want. It employed generic descriptions of operation semantics instead of writing rules for every op. And we also supported incremental partitioning, so do propagation partitioning in rounds. So the way it would look is that you would say, here's my training step, here's my mesh, and then you could give a schedule. And the schedule would say, partition these inputs on this axis. Then if you want, apply automatic partition on this other axis. And then if you want, shard the optimizer state on this axis again, for example. So it was a very simple user-driven schedule. I'm going to ignore these things. And the way it worked was that you would ingest the program and the schedules from JAX. You could go to our compiler stack that would do rewriting. For the automatic partitioning tactics, we had a simulator to simulate the communication and compute cost. And we'd have an AI agent, really a Monte Carlo tree search agent, using the information produced by this microsim to actually guide the search. And then we would lower down to lower level programs that would be able to run on TPUs and GPUs. And I'm just going to give you like just one example of what do I mean by this principled kind of rewriting of programs. If you think about a dot operator, a dot general, a matrix multiplication. So here's a 16 by 32 multiplied by a 32 by 64, returning 16 by 64. We were able to rewrite, we would give rewrite axioms that would rewrite this dot into smaller dots, into loops that had dots inside. So we would rewrite this program into a loop here of over two devices or two replicas if you want, where on every iteration of the loop you would slice the first operand, and then you do a smaller multiplication, and then you would, with this instruction here, you would return the stacking of all of these tensors together as a full tensor. So we have rewrite axioms that take dots and rewrite them into these loops or loops with reductions. So for example, if you slice the first operand on the contracting dimension and the second operand on the contracting dimension, you do a dot. The dot has a full shape, but you need to reduce, you need to sum all of these things together to get to the final result. So that was the essence of what we did. We didn't rely on this kind of propagation. We relied on taking the programs and rewriting them to have loops, fuse loops, propagate loops, create loops out of other loops, and only in the end take these loops and run them sequentially or run them in an SPMD fashion. And we had a generic description of this kind of behavior for every op. So we didn't have specialized rewrite rules for every op. We instead abstracted away the semantics of every op, which one is a contracting dimension, which one is a parallel dimension, and we wrote our partitioner based on that generic description. So I'm going to skip these things. So now the interesting bit for automation was that we can now define compiler action spaces. So you have X, and you can give a little action, a compiler API that says, please take this value X and create a loop out of it. We call this a dumb tiling loop because it just introduces a loop, doesn't really do anything on this value. But then the important thing is that the second action that we exposed was a propagate action, which says, if my operands are produced by a loop and I am not a loop myself, let me rewrite myself as a corresponding loop. So this amounts to the propagation stuff. So basically, we have these tiling actions, propagation actions, and now that's very nice because user tactics at Python level desugar to sequences of these actions, and also agent-driven decisions amount to generating like long sequences of this kind of tiling and propagation actions. And this is what the ML system experts used in the context of Deepmind, and this is what the wide range of ML researchers who didn't have ML experts in-house used. So we kind of targeted both. And automation really worked well, and the reason that it worked well was because we sort of tried to mimic the way a user would shard a model. You know, how would a user shard a model? You receive a model with like 500,000 operators. How do you shard it? It's kind of infeasible to ask the agent to take a sharding decision for each and every value of the model. It's kind of stupid. Instead, the user would have very, very good intuitions about how to do it. They would say, haha, let me shard my parameters on this axis. Let me shard my batch on that axis. So the user seemed to be working on the assumption that there are a few values that are important, the inputs of the function, that if you shard these, the rest will follow. And effectively, that's what we built. Then that's what the propagation action was doing, really. Right. So lowering part IR loops either sequentially or temporally. They're loops in the end, so it doesn't matter. And we built our compiler using an open source, great tool for infrastructure called MLIR. But maybe it doesn't matter too much. And we partitioned, and we moved the partitioner outside the compiler, which was really, 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 really good idea. Because now our partitioner can target other accelerators. We can modify it without bringing in the whole compiler legacy and thinking about the interaction with other internal compiler passes and invariants. And then the incrementality was very, very good. So we have this kind of schedule abstraction. Instead of having these sharding annotations, we had this schedule abstraction where you say, first do this, then do that, then do that, then do that. And it turns out that we compared that with the heuristics implemented in the GSP compiler, and that was better than just using the heuristics. All right, so we have some current partitioning work beyond SPMD partitioning. You want to talk about often data flow graphs of SPMD computations, and that means that you need to have like multiple programs, and each program should be an SPMD program, and we're working on that. We're still working on automatic partitioning for SPMD, particularly on how do we discover internal interesting sharding decisions, like the sequence length decision that I described before. And we have a new partitioner that incorporates the best of the legacy partitioner from Google and the legacy partitioner from Deepmind, GSPMD, and PartIR. And it has just been open sourced, actually. Right, and I think with this slide, I would just want to close. So the AI compilers is a very interesting space. The programs are very simple, superficially, but quite complex to actually partition, to actually do interesting things with. But this experience has taught us several things. We should try to build compiler components, not monolithic compilers that do kind of one thing, pluggable passes because teams have different needs. Action spaces, compiler action spaces all the way through. So typically we do not think of compilers as taking actions and evaluating using some metrics, but I think that's where we're heading. Progressive use of search and AI, so hierarchical and learned cost models, things like Monte Carlo tree search or reinforcement learning, deep learning, but also more new things like LLMs for synthesis of low-level codegen or testing and more. And then our compiler passes now should somehow have a more tighter integration with data. We've been compiling programs since, many decades, especially our C compilers, but it's kind of ridiculous that we have not learned many of the transformations. And there should be more opportunity for being able to take, especially in companies that have unified build systems and compilers. All that data of compiler optimizations, testing, performance evaluation should be used and reused to improve the compilers in a continuous form. I think, yeah, that's it. Yeah, thank you very much. This is what represents the work of many.
Thank you very much. Any questions from the audience? Do we have
hello, thanks for the presentation. How does partitioning work when the dimensions of the tensors given are not modulo 2?
So typically the systems will pad automatically under the hood the remaining chunk, and it will become regular and will be divisible. So there's a program transformation really that takes the program, pads the dimensions appropriately, and then shards.
And this even happens when maybe a device goes offline or something like that. Is this handled dynamically?
Interesting. No, well, I think in our settings it doesn't happen dynamically. In the context of really large training, this is actually, it's important to do something like that. In the context of the Google compilers, we deploy one program really on all devices. So it's kind of difficult. So this can happen through recompilation of a program for smaller. So you can imagine recompiling a program if something fails. The other thing with padding is that padding is interesting because you are now, if you pad, sometimes you pad too much. So you might introduce zeros and computing with zeros, or you might lead to some pretty unpredictable solutions for the users. So in part IR, we didn't allow this thing. We said, the dimensions you shard should be exactly divisible by your access. This has been relaxed in GSPMD and Shardy. There are trade-offs. Yeah.
Any other questions?
Thank you for your very interesting presentation. My question is, it seems that you assume that all computations will take the same time. Is this really the case in such large systems? Is there any space, any room for dynamic adaptations?
So in the SPMD partitioning sense, it is the case. But it's an artifact of partitioning, right? What ends up happening is that sometimes when something is not partitioned well, it gets replicated on all devices. So that cost everyone pays for it. And there is a hidden cost of SPMD, which is kind of interesting, which is you have 10,000 devices running, and one of them becomes slower for, let's say, a network issue. Something, there's a hiccup in a switch or something, right? A few of them become slower. All of them pay for it because you need to reach kind of a global synchronized rendezvous. So SPMD has this kind of hidden cost that we should be breaking out of, and that's the MPMD work that I described in the end of the slide. We are extending the SPMD partitioner to also include data flows of computation. So now you can think of, you have one cluster of one set of devices, different dimension, potentially another cluster, different set of devices. Computations can take different amount of times, but you try to balance them. So it simplifies things to think of them hierarchically. At the low level you have SPMD, at the higher level you have MPMD. Just as a means of taming the complexity.
Thank you.
Any other questions? Let me ask one then. Oh, yeah. You have been talking about training, right? What about inference? Because there have been studies showing that, in the longer term, the inference cost is also very important. So do all these ideas apply?
Yes. Some of these ideas apply because inference models are smaller. The sharding for inference is important, but it's I would say maybe a little simpler as far as the sharding concerned, because you have a smaller cluster of devices that you send requests to. But the problem there is that you have if you want to put it as a service, when you want to multiplex requests from multiple users, and also that parts of the computation have different compute characteristics. Filling in the context cache versus actually, generating the next token. There are different computations with different characteristics, so the space of sharding, or I would say partitioning, or maybe distributing is the right word for this. The computation is more interesting, more greenfield, I would say. For training, it's very regular. For inference, so some of that stuff applies. You do need some SPIMD in the end of the day, but you need more stuff, a lot more stuff around it.
Yeah. Petros.
Another question, maybe a little bit broader than this particular thing. So when people develop software and do software engineering, there's particular patterns that people follow over the years, like the agile pattern and so on. And I was wondering if you could comment what kind of software engineering practices exist now in this machine learning community. Maybe that's a loaded or too broad, but if you have a few comments.
Yeah, so there are different things. Like, my team is an infrastructure team. So we build, we build tools, compilers, runtimes. Then there's the ML team, who is implementing new features in the models and evolving the models and doing evaluation. And I don't know about their model of operation very well.
But the software, who does the software?
All of us.
All of you?
Yes.
Do you follow any particular patterns or anything goes?
No.
Anything goes?
No, I mean, we have planning and I think kind of experience. I would find a very hard time labeling what we do, but I can explain what we do, which is typically, at least in infrastructure teams, we typically propose a feature that we want to implement, or we have discussions with the machine learning researchers. There's this form of sharding, for example. We propose a feature, we write design documents about how to actually do it, and we start prototyping, and it evolves kind of from that. But there's like many of these at the same time, and often new design documents kind of happen organically. People just say, oh, I have this idea, I'm going to propose it. It gets brought up for discussion, and people start working on it. I don't know if Yannis is around and would have something to comment about the ML side of development.
Probably not right now. We have time for one or two questions. Any more questions? Here's another one from me. To what extent are these tools and ideas Google specific? So are the other big players also using similar tools, or are all these tools shared?
So I would say that partitioning is, I think this technology is, there are parts of it that are general, but parts of it that also are a little bit over-indexed on the way things have happened traditionally, historically at Google. At Google we did have traditionally, these big pods, fast interconnect. So SPIMD partitioning seemed to be like kind of very, very good fit for these kind of things. So there's a bit of an over-indexing, I think, on SPIMD partitioning, because it works in our settings. And I think in the PyTorch, and also a bit of over-indexing on compilation. So, what I described here is, you trace a big program and you compile the whole program. Whereas in the GPU world, in the open source world, it's not quite always like that. You typically rely on more dynamic dispatching of CUDA kernels and the CUDA communication primitives. But I think the concept of partitioning, if you have a regular topology, I think that part, the SPIMD partitioner, is a universal concept. And we have had a bit of reach out from various industrial partners outside Google who like the abstractions and think that abstraction would be good for them. So yes and no, some parts of it, yes.
Thanks. Any other questions? If not, we can thank the speaker again.
Thank you very much.